Hello everyone, welcome to another session on statistics. So today we are going to cover a very interesting area of statistics, and from my experience I have seen a lot of people struggling with this particular concept. So today we are going to cover hypothesis testing, and we will look at what a null hypothesis, what an alternate hypothesis, under which scenario do we do hypothesis testing, and how do we use null hypothesis and alternate hypothesis in making a statistical assumption or hypothesis being declared as true or not true. So let's get started. So let's look at hypothesis testing. So as I have said in my previous lectures, that whenever you're trying to learn a particular topic, try to understand the meaning of each word. So here we have two words, hypothesis and testing. So if we try to dig deeper, hypothesis means what? Some kind of belief, some kind of assumption, some kind of intuition. Now this belief, assumption, intuition, whatever we have, we need to do some testing and see whether these belief, assumption, intuition are, whether they are valid or not, whether they have got some base or not. I can never say whether it's true or not, but we can see what's the probability of this belief, assumption, intuition being true. How likely are these to be true? Fine. Now what we will do is we'll try to do some testing. So the answer to this question can only be done through some testing, right? So we have some belief or assumption or intuition, and we want to understand how likely are these belief, assumption, intuition to be true, right? Through some kind of testing. What kind of testing? Some kind of statistical testing. Let's go step by step. Some kind of statistical testing we are going to perform. So now let's understand what are the two main pillars of hypothesis testing. And even before that, let's go through a scenario and let's try to understand how a belief or an assumption or an intuition gets formed. So suppose you go back to the time machine in 2019. Actually, we want to go to 2019 looking at the current scenario. Jokes apart, so suppose you are in 2019 and you have an hobby of visiting your friend's place over the weekend. So every weekend you go to a friend's place to chill out, to have some nice time during the weekend. But the statistician within you, it refuses to give up. It always tries to find something. So what do you end up finding? So you go to your friend's place and start observing how the kids are leveraging their weekends. So suppose in 2019, you went to 50 friends' place over the weekend. Maybe 2 weekends you kept for yourself, which is fine. So you visited 50 friends, and what you observed is that out of these 50 friends whom have got kids, 40 kids are watching TVs. Okay? So suppose this is your universe, this is your friend's universe. Right? These are the 50 friends you have got. So you start making an assumption based on these 50 friends, which in your case you can think of being population. In your case, by the way. So you can think, okay, around 80% kids are watching TVs, right? So 40 by 50 is 80%. So you make an inference that around 80% kids are watching TV based on what you have seen. Fine, no problem. This is okay. Now, you are in 2020. And after all lockdowns and social distancing will still stay. After all lockdown got relaxed, you started visiting your friend's place again, of course maintaining social distancing, and you again visited. You have made more friends this year, so you have few more friends, and this year you went to around say 30 friends place. Now this time here you had 70, you have 50 friends. So in this case, in 2019 your number of friends was also 50. So in this case, consider this as a population of friends with your context. In 2020, suppose you have got say 70 friends, you have made 20 more friends, and you have gone to 30 of your friends' place over the weekend, right? So total number of friends is 70. That's total number of friends, total friends, right? So you have visited 30 friends and you found that 18 kids are watching TV. So now the statistician in you has become very inquisitive. So you started analyzing these two incidents. And this time you have seen that around 60% kids are watching TV. So I can say here around 60% kids are watching TV. Okay, fine. So now let's look at these two incidents. So now let's understand these two incidents. If we look at and compare these two incidents, what is the first thing which strikes us? That probably kids are watching less TV, right? But watching less based on what context? What is my base assumption? What is my base, not assumption, what is my base data? My base data is this. So whenever I am seeing less TV, it's always compared to your base data, or you can also say population, right? So from your base data and the current data, so your baseline data and the current data, when you analyzed, your analysis says that probably kids are watching less TV, which you have seen from here, but you are not sure. Why? Because you have not visited everyone. You have only visited 30 friends out of your 70 friends. So now the question which comes in your mind is, okay, I have visited 30 friends and I have seen around 60% kids are watching TV. So let me make an intuition that kids are watching less TV. Now, if we have to represent this intuition mathematically, in mathematically there is nothing like less and more. Everything has to be represented through a number. So let's try to represent this mathematically. And the mathematical representation is so the mathematical representation is mu1 greater than 80%. Mu1, just consider any other variable. Okay. So that is what my hypothesis is looking at these two data, right? So now my intuition is that people are watching less TV from where? From 80%. So if I have to represent it mathematically, my mathematical representation is H1 is equal to mu1 less than 80%. Fair enough. So what is the alternate, or what is the reverse of H1? If I have to make a reverse logical statement and a mathematical statement. So the reverse logical statement of what we have seen is that kids are watching more TV. My belief is kids are watching less TV, but the reverse of it is kids are watching more TV, right? So from here, we can now understand null and alternate hypothesis. So let's keep this example in mind. So what is alternate hypothesis? So it's generally what we believe and something which represents a change. So what we believe okay. So alternate hypothesis is what we believe and it also represents some kind of change. Actually, this is not a question mark. So if you look at this example, what we believe that kids are watching less TV, and the moment we are saying less, that's a change from my baseline data, right? Had we observed 24 people here, 24 kids watching TV, then I would have said 80% kids are watching TV and there is nothing interesting happening here. So I really don't need to bother. Nothing has changed. So here what we see is a change. Here it's at 80, here it's 60. So there is a change. And that change is driving a belief. Right? So that change is driving a belief. What is my belief? This is my belief. So alternate hypothesis is something what we believe. And when we are really bothered about this belief, when there is something interesting. When there is something interesting happening, there is some change in the system which makes us believe something, right? So that is called alternate hypothesis. Now what is null hypothesis? So null hypothesis is just the reverse of alternate hypothesis. So for example, we had said that mu1 less than 80%, right? So the null hypothesis in this case will be mu1 greater or equal to 80%. Just the reverse of alternate hypothesis. Something which we do not believe, right? Which we do not believe. Okay. Now how to remember it easily? Look at the word null. Null means nothing, not my hypothesis, right? This cannot be my hypothesis. So not my hypothesis, null hypothesis, right? So we have two statements now. One is what we believe and one is what we do not believe. So alternate hypothesis is what we believe, null hypothesis is what we do not believe. Also remember, the entire hypothesis testing comes into picture and we start building hypothesis when we see some change in the system. If there is no change, I really don't need to bother. So we have got a null hypothesis and an alternate hypothesis. So we have a null hypothesis and an alternate hypothesis. So from this alternate hypothesis, I have formed a statement, and somehow my intuition, my assumption, my gut feeling, which is my alternate hypothesis, I want that to be true. I want to prove that true. Right? Here, I want to prove that kids are watching less TV. Here, less is from the baseline data, as I said, which is 80%. So I want to prove this true. How can I prove it true? Through my hypothesis testing. So in hypothesis testing, what we do is we try to test the alternate hypothesis. Which in this case is mu1 less than or equal to 80. Sorry, my bad. Not, there's no equal to here. So we want to test this to alternate hypothesis. Rather, we want to test this alternate hypothesis through hypothesis testing. Now I have a problem. The problem is, in statistics, there is no such test through which you can test an alternate hypothesis. Problem. So, at least till now, we cannot test this. There is no such tests available through which I can test my alternate hypothesis. So this does not work. Okay, then how do I prove it? I have something called null hypothesis. So here I have a null hypothesis. So note that I have made a notation of H0 and H1. H0 here, this signifies null. Right? This is not a 0, this looks like a sigma. So I have a null hypothesis here, which is signified by H0. And my null hypothesis is mu1 greater or equal to 80%. Now in this case, it's, if you look at these two, it's not possible that it will be greater than 80. So worst case scenario, it can be equal to 80, but cannot be greater. So let's make it equal. So see, we have null hypothesis, which is another weapon. So what we can do is, there are some tests available through which you can do hypothesis testing using null hypothesis. Fine. So I cannot use alternate hypothesis to do hypothesis testing. I can use null hypothesis to do hypothesis testing. And here starts the fun. I want the outcome of this null hypothesis not to be true. Now in statistics, and especially in the world of probability, we cannot really say true or false. We can at least say that it has a high chances or it has low chances, or the probability is high or the probability is low. So in this case, what is my aim? What is my objective? My objective is that when I do the statistical tests, I want the probability of this particular statement to be very, very low. I repeat, when I do hypothesis testing, I use null hypothesis, and I want the outcome of this statement, which is the null hypothesis. This statement should have very low probability. This statement should have very low probability. Which is strange, right? So now the next question comes is, fine, high, low, I understand, but if it comes low, then what happens? If it becomes high, then what happens? If null hypothesis becomes high, then what happens? Right? So you have a lot of question in mind. But before that, let's understand something, that in the world of data, there is nothing called high or low. Everything is numbers. So when I say low probability, what does a low probability means? In this case, generally, with hypothesis testing, we say that the low probability can be said about an event if its chances of occurrence in reality is less than 5%. Generally, there can be some exceptions. Someone can explicitly mention some percentages, but if nothing is mentioned, always assume that when we say low probability, we mean that the chances of occurrence of that particular event is less than 5%. Now, if you recollect what we had learned in our previous videos, this probability is also denoted as p-value, which means this p-value should be less than 0.05. P-value is not calculated in terms of percentage, but 5% is nothing but 0.05 only. So if you recollect our last video, we had actually showed you how to use z-score and get a p-value. P-value is nothing but the probability of certain thing or a certain event being true. So the probability of the kids watching TV, rather I would put it like this, the probability of 80% kids watching TV in reality should be less than 5% if I want to establish my belief. What is my belief? That they are watching less than 80%. So in this case, I have to, or rather I will expect, I will hope that when we run some tests, we will find that this particular statement has got very low probability or very less chances of occurrence. Now, why are we doing this test? As I have mentioned before, because I have not visited everyone, else so I could have passed a judgment. Here I am not able to pass a judgment because I have not visited everyone. I have only visited 30 people. Now the question which comes is, the way you have to think about this is, that is this number 30 and this 18, right? 18 out of 30 kids watching. Is it enough to make an inference? Right? Is it enough to make an inference? So when I'm interested in this kind of inferences, when there is some kind of change. Here we have seen some changes. But is the change enough? Because I'm only talking to 30 people. I'm not talking to the entire population, right, of 70 people. So the results which we get for 30 people, is it enough to say that the same will apply for 70 people also? Okay. So now, how do I do that? Using hypothesis testing, where we have a null hypothesis, we have an alternate hypothesis. So now let's take a scenario, and that will probably make things more clear. So suppose I have a hypothesis to test that let's start with H1, that mu1 less than 70. Now what is this 70? 70 or 70% or whatever, right? What is this 70%? Say 70% people ordering pizza over a weekend, right? So we analyzed again data of two distinct time frames or two different observations or set of observations. So in 2019 or in 2020 Q1, you again spoke to few of your friends and just asked them casually, do you order pizza during the weekend? So you have 50 friends and you asked all of them, and 70% people said yes, we do order. In Q2 2020, you were not able to connect to everyone, so you asked 20 people, 20 friends, and they said so 50% of them said that yes, they order, which means 50% say that they didn't order during this frame. So my baseline data is this, right? And I can see that there is a trend. I build a hypothesis that probably people are ordering less pizza. What is less? From where? From this 70%. So mathematically representing mu1 is less than 70%, and that is my alternate hypothesis. Here I have observed a change, a strong change rather, to make some kind of assumption, right? And in this case, my null hypothesis is that my mu0 is ideally should be greater or equal to, but in this case it cannot be greater in any case. So let's be lenient and let's put equal to. So now, as I said, I cannot test H1, so I can only test H0. So now I will suppose do some tests. What tests? Don't worry about it right now. We'll look into it detail. So suppose we have done some statistical tests, and the outcome of these tests are nothing but p-values, right? P-value means the probability of something being true. So here, for this scenario, suppose we got a p-value, and here also we got a p-value. Suppose this p-value is 0.04. So ideally, this p-value should be 0.96. If this is 0.04, of course, this will be 0.96. And just to make things logically good, so now it should be like it has to be a binary condition. Either it's less than 70 or greater or equal to 70, right? Though technically we can see that here the greater part doesn't really matter. So if I have got a p-value of 0.04 for my null hypothesis, then my p-value for alternate hypothesis will be 0.96. Now what does this signify? So ideally, if the p-value of your null hypothesis, which we can test, this we cannot test, by the way, this we cannot test, but this we can test. So if we can get the p-value of H0, we can also derive the p-value of H1. So this cannot be directly achievable through statistical tests. We achieve the p-value of H0 or the null hypothesis, and from there we can extrapolate alternate hypothesis if the conditions are made binary. That's the reason why, just for your understanding's sake, I made it greater than equal to and less than 70. So now I have a p-value for null hypothesis. I have a p-value for alternate hypothesis. If this p-value, as I said, goes below 0.05, then I said, hooray, I have made a failed experiment. So here my experiment can only be done with H0, not H1. And I want this experiment to fail. I want H0 to fail and give me a very low probability, right? How did you calculate? If you think, okay, chalo, how did you find this 0.04, 0.96, 0.55? Right now, I've just cooked it up. How do we actually do this test? Let's not worry right now, but let me just give you a spoiler alert. It's not very difficult because by this time you already know central limit theorem. So now we have got a p-value of 0.96 and 0.04. Now this 0.04 is less than my threshold, which is 0.05, until specified, as I said, in statistics. It's 0. This number, this threshold, we always consider as 0.05 until and unless specified. Where do we specify? Say, for example, in healthcare, for very sensitive tests, probably they want this 0.04 to be, say, 0.001 because there's high chances, right? So the p-value of 0.04 means that there is only 4% chance that this particular statement is true. If that is the case, then the chances of this person or this statement being true has to be 96%. So my objective was to test the alternate hypothesis, which I cannot do directly. So I will test through null hypothesis, do some calculation, get a p-value, and then look at whether the value of this p-value is less than 0.05 or not. So in this case, we see it's 0.04, which is less than 0.05. So in that case, what we can do is, we can say that, sorry, Mr. Null Hypothesis, we have to reject you. If that happens, so I have to accept the alternate hypothesis which I always wanted. So I wanted to accept the alternate hypothesis, but that was not possible directly. So I want that the probability or the p-value of the null hypothesis becomes as low as possible. And that's my best chance that my case will get pushed. What is my case? Alternate hypothesis. So now let's look at some of the outcomes of null hypothesis and alternate hypothesis. So let's open Excel. So we'll say null hypothesis p-value alternate hypothesis p-value. And here outcome of null hypothesis and the outcome of alternate hypothesis. Which is not required to save this. So now say my null hypothesis is 0.04, which means my alternate hypothesis is 0.96. So outcome of null hypothesis is reject null hypothesis. And this is rejected. We can say that we can accept alternate hypothesis. So now let's take another scenario, say 0.58, right? So, or rather let me put it, say 0.07. So this becomes 0.93, right? So in scenario 1 or in row number 2, the null hypothesis, the p-value of null hypothesis is 0.04, which automatically means that the p-value of alternate hypothesis will be 0.96. So in null hypothesis, suppose it is now 0.07, which means alternate hypothesis is 0.93. Now what do we do? Right? So in previous case, I rejected the null hypothesis since it was, the p-value was very, very low. And I accepted the alternate hypothesis because the p-value is very, very high. In this case, 4% and 96%. Now for null hypothesis, if this is 0.007 and this is 0.93, then what happens? So can I reject the null hypothesis now? Unfortunately, no. Because I had said that this is the range, this is the number or the matrix which we should take as baseline, right? For any statistical tests. So now here we can see that the p-value of the null hypothesis is quite low, or rather not quite low. It is 0.07. So in this case, what shall we do? Can we reject the null hypothesis? No, of course we cannot, because it is 0.07 greater than 0.05. So we cannot reject the null hypothesis. So then we can accept the null hypothesis, right? If we cannot reject. And in this case, we can say reject the alternate hypothesis, right? Unfortunately, not right. And this is where a lot of guys make mistakes. So pay attention here. Here, can we reject null hypothesis? No, we cannot say that. Can we accept null hypothesis? No, we cannot say that either. Why? Or rather, can we reject null hypothesis? No. Can we accept null hypothesis? No, we cannot. Why? Because if you look at it intuitively and carefully, still the chances of the null hypothesis being true is only 7%. Now, how can you accept something whose chances of occurrence in reality is only 7%? So in this case, I cannot reject null hypothesis. Neither can I accept the null hypothesis. Why? Because as I said, the chances is only 7%. So what do I do? In this sort of scenarios, we project like this: fail to reject null hypothesis due to lack of statistical relationship or whatever, right? So in this case, we cannot reject the null hypothesis, but we cannot accept it either, because its chances of occurrence in reality is very, very low. It's only 7%. So my answer is, we will say in this scenario, we'll say we fail to reject the null hypothesis, which means I do not have enough evidence against my null hypothesis, right? This 7% is not a good enough rational, right? Only 7%. So we cannot accept, rather we cannot reject null hypothesis, but not can we accept the null hypothesis either, right? So this is 7%, and we say that fail to reject null hypothesis due to lack of statistical relationship, evidence, whatever. And here we can say we do not have enough evidence to prove alternate hypothesis. We can only prove alternate hypothesis if we reject the null hypothesis. In this case, I am not rejecting, right? So if I am not rejecting, I cannot make the alternate hypothesis reject as well. By the way, it's a spelling mistake, right? So in this case, we say fail to reject null hypothesis, right? Now the question is, if you ask for an example, like for example, in law, a lot of times we say that we are letting this criminal go, though we know that he is a criminal, but we are letting him go because we do not have enough proof against him. But we know that, he's a criminal. So that's the kind of scenario we have come now, right? We don't have enough evidence to prove that the alternate hypothesis is true. We don't have enough evidence to say that the null hypothesis is false, right? So in that case, can we not ever accept a null hypothesis? The answer to that is yes, you can. You can accept null hypothesis. But under what scenario? So if the p-value is of the null hypothesis is say 0.96 for example, and this is 0.04, right? So in this case I can come and say yes, we can indeed accept the null hypothesis. Why? Because we have high p-value for null hypothesis. So in this case, null hypothesis, the p-value of null hypothesis is very high. And in this case, 96%, right? If I can reject it below 4%, I can also accept it above 95%, right? So in this case, if my p-value is greater than 0.95, then I can accept null hypothesis and I can reject alternate hypothesis, right? Now, in reality, the chances of occurrence of this particular problem is very, very less. It's very unlikely that in your test you will find a p-value for a null hypothesis being 0.96. It will never happen, right? It's unlikely. Probable, but probably not possible, right? But still good to know. So our scenarios lie between generally these two conditions. Either we reject null hypothesis or we fail to reject null hypothesis. So later I'll also tell you that how come this is possible. I mean, under what scenario you can get a null hypothesis having a very high p-value, right? So to sum up a scenario with an use case, so here I'm not going to take a use case name or something, just think that mu1 greater than say 30 and mu0 greater or equal to 20. So mu1 is my alternate hypothesis, mu0 is my null hypothesis, okay. And I want mu0 to be having a p-value which is very, very less. Don't worry about this point, how am I getting this p-value? We'll do that in another video. Right now, let's just understand that we have some ways to do some statistical tests. We can gather something called a p-value, which is basically the probability of that particular incident happening. So here mu1 is less than 30, mu0 is greater than or equal to 20. Or rather, it should not be 20, it should be 30 only, right? Just the opposite of this. Now, if the p-value of this particular assumption is say 0.03, right? Then in that case, the p-value of here will be 0.97 or 97% or 0.03 or 3%, right? If this is the scenario, then what can I do? I can reject the null hypothesis and accept the alternate hypothesis, right? And if this is the scenario, say 0, 7 and 3. So if this is the scenario that the p-value is greater than 0.05 but not very high also, right? So in this case we can say that we do not have enough evidence to prove that null hypothesis is false, right? So we do not have enough evidence to prove that the null hypothesis is false, or not enough evidence to reject the null hypothesis, or not enough evidence to accept the alternate hypothesis. So now we have understood null and alternate hypothesis. So let's understand confidence interval in a bit more detail. So what is confidence interval? Now you have noticed that so far with all the tests which we were doing, I was saying that if the p-value is below 0.05, we consider the null hypothesis to be false and alternate hypothesis to be true. So let's write down p-value less than 0.05 means null hypothesis is not true. Right? Or rather, I should say the chances of null hypothesis being true is only say 2% or 1%. I said not true may not be the right term. So here let's understand from where did we get this 0.05. This is, by the way, called as the confidence interval, right? But why 0.05? So let's dissect this. Suppose you are captaining a cricket team and you are playing a 7-match series. You have gone to a different country and you are playing a 7-match series. So in the first match, you did the toss. First match you did the toss, you called heads and you got tails. So you lost the toss, right? So now in this case, what is the probability that you get a tail? The probability of getting a tail is 0.5% or 0.5 or 50%, which means in reality the chances of getting tails is 50%. By the way, you have called heads, you lost the toss, right? Second match, you again called heads and again you got tail, right? Now in reality, what are the chances that you get two consecutive tails? We will cover conditional probability later, but from here at least let's understand this in a slightly detail. I mean, in two match series, what are the different combinations which can happen? Head head, head tail, tail head, and tail tail. So the chances of getting two tails is 1 out of 4, which is 25%. So you lost two consecutive toss. So does that strike you that, hey, you know what, something is not right? Or you will feel, no, it's okay. I mean, two tosses, having consecutive tails, no big deal. Ideally, it's no big deal. It happens. I mean, two consecutive tails, what's the big deal, right? Third match, you again go. You again call tails. Sorry, you call heads, and you get tails. Now the chances of getting three consecutive tails is 0.125. If you just see the trend, it's just getting half every time. So the chances of getting three consecutive tails is 0.125, which means you have encountered an incident whose chances of occurrence in reality is 12.5% only. But do you doubt this scenario? You will say, no, I mean, it's okay. I mean, we can have. You go to the fourth match. You again call heads, and you know what? This time also you got tails. So what are the chances of getting four consecutive tails? It will be most probably 6.12%, 6.25, right? Let's just do the simple maths. 0.125 divided by 2, 0.625. Perfect, not 1, 2. Which is equal to 6.25%. So now you start getting a bit of doubt, because if you think logically, you have got a scenario where the chances of occurrence of something is 6.25%, and you have encountered that kind of scenario. You start getting a bit of doubt. Now in the fifth match again, you called heads and you again got tails. Oh my god. What's the chances? What's the probability? It should be 3.12% around, right? Now you have encountered a scenario whose chances of occurrence in reality is 3%, 3 point something. Now you think, boss, definitely something is not right, right? So these barriers below which we generally start doubting, the barrier is kept at 5% or 0.05, whatever you want to say. And this barrier is nothing but my confidence interval. Now, is it every time that it will be 5%? Not really. I mean, in some cases, as I said before, that especially for medical cases, this confidence interval is taken to say 1%, right? 0.01, because we are dealing with someone's life and death. So we better be sure 99% about our alternate hypothesis. But this is, in general, we use this. Okay. In general. Now let's understand what are the different varieties of tests which we can do with hypothesis testing. So what are the different varieties of tests? We do z-test, we do t-test, we do few other tests which I'll cover in probably a subsequent video in detail. One more area of tests which we do are called one-tailed test and two-tailed tests. So what do we do in one-tailed tests? What is the property of one-tailed tests? In case we are dealing with greater or lesser, that means I'm checking only one side, right? In two-tailed tests, we are checking equal and unequal, right? So for one-tailed test, we check if something is greater or lesser. For two-tailed tests, we check equality. So let's take some examples. Suppose I have an alternate hypothesis that the average age for doing gym is, say, less than 30, and the equivalent null hypothesis will be right. So here the alternate hypothesis is the average age is less than 30. The null hypothesis is the average age is greater than 30. So here we are checking only one side. Likewise, if you do say the average IQ of people, suppose we make an alternate hypothesis is that it's greater than 110, for example. So in this case, the null hypothesis is right. So here we are, in both these scenarios, we see that we are only testing one side, and this is called a one-tailed test, when we are usually checking either the greater or lesser. Now when it comes to two-tailed tests, let's look at Let's look at two-tailed tests. Suppose I say that I have made some decoration changes in my shop, and I have seen that the average footfall has changed, or the change can be increased as well as decreased, right? So that I can say that the average footfall has changed. So say in this case I say, okay, my alternate hypothesis is that the average footfall, which previously was 30 per day, is not equal to 30. And the null hypothesis is that the average footfall is equals to 30. How to do these tests we will discuss in detail, but right now let's just understand this part, that two-tailed tests denotes equality or not equality, inequality. One-tailed tests check for greater or lesser. Okay, so now we have understood null hypothesis, we have understood alternate hypothesis, we have understood confidence interval, we have also understood one-tailed test and two-tailed tests. Now let's understand something which is very interesting, and we call it as confusion matrix. In the next video, I'll cover in detail about the different varieties of tests which are available, Z-test, T-test, and there are a few other tests also which are non-parametric in nature, and I'll explain them in detail, don't worry. So now let's understand something called confusion matrix, which is confusing. So what is a confusion matrix? So right now, forget null alternate hypothesis for a moment. Let's concentrate only on this as a standalone scenario, and then later we'll find the relationship of confusion matrix with the hypothesis testing. So in confusion matrix, we look at the actual value and the predicted value. Okay, so we look at actual value and the predicted value. So suppose here we will consider a scenario where, suppose we are trying to predict whether a particular person is likely to have diabetes or not. So in this case, if the person is diabetic, we are denoting it with 1. If the person is not diabetic, we are denoting it with 0. Okay. So suppose we have around few observations. Let's see how many I can fit in here. So we have these many observations. So let's give it some numbers because that will help us later on. So we have 9 observations. Okay. For say for 9 people, we have got the data. And now what we want to do is we want to make some prediction on this data. We do not know what is the actual answer. We look out for some other parameters like his blood pressure level, his height, weight, etc., etc. And we just try to make a prediction whether this person is likely to be diabetic or not. We have got some data where we already know the answer, whether the person is having diabetes or not. And before we really make some prediction on real data sets, we first want to do some testing. So in this scenario, suppose we predicted after doing some tests, what tests and what, don't worry about it right now. Suppose you did some tests and then you predicted, okay, this is 1, this is 1, this is 0, this is 1, this is 1, this is 0, this is 1, this is 0, and this is 0. So looking at the characteristic trends patterns, you have made these 9 predictions. Now out of these 9 predictions, how many have we got right? Let's understand that. So how many are correct? This is a correct prediction. Let me use a different ink. This is a correct prediction. This is a correct prediction. This is a correct prediction. This is a correct prediction, and this is a correct prediction. And what are wrong predictions? So this is a wrong prediction. Wrong. Wrong. And this is also correct, right? So as you can see here, why wrong? Because the actual value is 0, which means the person was not diabetic. However, we have predicted him as diabetic. So here the actual one is 1, which means the person was diabetic, and we also predicted diabetic, fine, and these are all fine. Here these 2 records are where the mistake has happened. This is where the mistake has happened. So here, as you can see, the actual is 1, which means the person was diabetic, but we didn't predict him to be diabetic. Here the actual person was not diabetic, however we said that the person is diabetic. Now in confusion matrix we have 4 concepts. True positive, true negative, false positive, and false negative. So true positive means when, first of all, let me give you a shortcut on how you can remember this. So this right hand side, these positive negative ones, you always assign it to 1 and 0. So let me just put it here. So 1 is positive and 0 is negative, right? And that also makes sense, right? 1 is a positive positive prediction, 0 is a negative prediction. So true positive means that in this case, as I said, first look out for the positive predictions we have made. Positive predictions means where we have made predictions as ones. We have predicted, right, this side. So this is what we have predicted: 1, 1, 1, 1, 1. These 5 scenarios we have predicted 1. Those are positive predictions. Now, out of these predictions, how many are true? How many correct predictions have we made? These true or false means this T and this F means correct and wrong. Right? Now we'll answer looking at this formula. It will be much more simpler. So for the first one, let's find out how many true positives are there. So for that, first we'll figure out how many positives are there. So 1, 2, 3, 4, 5. Out of which, how many we have got right? We have got right in 1, 2, and 3. Right? So 3 of them are right. So my true positive is equal to 3. Now let's look at the ones where we made a positive prediction but that came out to be wrong. So in this case, that is called false positive. I have made a positive prediction which is false, which means this one, this record, and this record, 1 and 7. Two false positives, right? And what are the true positives? True positives are 2, 4, and 5. Now comes true negative. How many true negatives are there? Or rather, how many negatives are there at the first place? So let's look at the negative ones. So this is a negative prediction where I predicted 0. Negative prediction, negative prediction, and negative prediction. So these are the 4 negative predictions we made. Now out of these negative predictions, how many are true? How many are correct? This is correct, this is correct, and this is correct. So true negative are 3. The ones are 3, 8, and 9. And what is how many false negatives? Only one. That is row number 6. So here we have made 3 true positives, 3 true negatives, 2 false positives, and 1 false negative. So if I have to calculate the accuracy of my prediction, that will be equal to true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. So here, how many true positives do we have? 3 true positives and 3 true negatives divided by 3 plus 3 plus false positive are 2, false negative are 1, which is equal to 6 by 9. If we get this in terms of percentage, 6 by 9 is around 66.67%, right? So this is all about confusion matrix. So if you have to just write one line about confusion matrix, true positives are what? I predicted true, right? I predicted, or rather, let's write something like this, something positive. It became true. True negative is I predicted something negative. It became true. False positive is I predicted something positive. It became false, right? Or rather, let me write it like this: the prediction became true. The prediction was true. And false negative is okay. So false negative is I predicted something negative and the prediction is false. All right. Now later we'll see how this can actually get connected with the hypothesis testing. Okay. So let's just take one example. Say, let's take an example of a credit card fraud. So true positive is what? So in this case, credit card fraud is 0, not fraud, 1, fraud. So true positive is I predicted fraud and it was indeed a fraud for a particular record. True negative is I predicted that it's not a fraud and it was indeed not a fraud. False positive is I predicted that it's a fraud but it was not a fraud. And false negative is I predicted that it's not a fraud but it's a fraud. Now you think logically, for this problem of credit card fraud, out of these 4 scenarios, which one is more dangerous? if we think the most dangerous scenario in this case is false negative. Because I said it's not a fraud, it's okay, no problem with this transaction, and it turned out to be a fraud, which means the organization will lose money based on your prediction. Okay. Now, what we shall do is, we'll do a quick recap of whatever we have learned so far in this session. So we have learned about null and alternate hypothesis. We have learned about confidence interval. We have learned about one-tailed and two-tailed tests, and we have learned about confusion matrix. So we have learned all these things. If you like this video, do subscribe to the channel and let me know how is it going. If you want to enroll for the course, you can click on the below mentioned link and join the wonderful journey of data science. So till then, all of you keep learning, happy learning, and I will see you soon with the next series of lectures in statistics. Thank you everyone for watching this video.
To know more, follow and subscribe to upGrad.